Lecture 7.3, Wave Interference Due to Path Difference. In our discussion so far of wave interference, we have not stated how a wave gains a phase. We just stated it. The most common way to get a phase difference is by path difference. So here's what we want to do. We want to envision two sound speakers separated a linear distance delta R. We expect these waves to superimpose at some point up ahead. This point is called the observation point P. So let's draw our system here. So I imagine that I have a speaker, and for the sake of argument, I'm going to color this one blue. And I'm also going to label this 2. And then I'm going to have another speaker which I'll color this green, and I'm going to call that speaker 1. So when I say there's a separation, I'm going to say that that these two are separated by delta R. Now, what I'm going to do here is that I'm going to come in and I'm going to pick my observation point. So there's going to be some observation point, P, right here. Now, when I look at this, note that there are two distances. There's this distance from here to here. So this travels a distance R1. This one travels a distance R2. So R2 travels farther than R1. So now what I'm going to see here is that these are the waves coming from speaker 2, and these are the waves coming from speaker 1. And so they're going to overlap at P, and we're going to have interference. So interference will occur if the phase due to this path difference is, it's going to be B, and then I'm going to have two waves or two different paths, which tells me that this is R2 and this guy is R1. And this is typically written with delta R like this. Now, this is an important equation. Okay, and this is what I call the path difference equation. Maybe I should call it the phase path difference equation. And this guy is very important. So you want to understand this one well. So now what we want to do here is we want to go in and we want to interpret this. Okay. So now we want to interpret this relationship. And we'll do this in steps. So here we go. 1. What path difference is required to cause constructive interference? Earlier, we showed that for maximal constructive to occur, the phase had to be multiples of 2 pi m. So in other words, if I look at my phase, if I want constructive, it has to be 0 plus or minus 2 pi plus or minus 4 pi. And this was 2 pi m, where m is equal to 0 plus or minus 1 plus or minus 2. Now, because this is constructive, I'm going to put a little c here. It makes sense initially, and then we want to drop the c later on. Okay, so this is what we've already stated. So from the phase, from the path difference equation, we write that the phase for constructive must be 2 pi m. Remember, I'm going to put a little c here, and this has to equal to 2 pi lambda times delta r, which then says that the path difference, in order to be constructive, has to be values of mc lambda where MC has to be 0 plus or minus 1 plus or minus 2, etc. So the phase equation and this path difference are really one and the same thing. It's easier to interpret what we mean by path difference to see what our picture should look like. So, how does this picture of delta R constructive mean? So here we go. So the first thing that we'll look at is we're going to look at MC equal to 0. That immediately implies that the path difference has to be 0. So that means that both speakers are lined up together. So if I look at them, I'm going to say that I have a speaker here. And of course, I have my second speaker, and the path difference between these two is 0. So when I look at my blue one, and I look at my green one, they're going to be emitting waves. So I don't remember how I labeled these. So the blue is 2. So then this guy is 1 and 2 here. And you could see here, so if I look at the edges right here, they're lined up. So then delta R is equal to 0. So then that means here is that this guy is going to emit a wave. And then this wave, this source is going to emit a wave as well. And you could see that as they emit these waves, these guys are in phase. They're right on top of each other. So the phase, so when I look at this thing, we immediately see that the phase, so the path difference equation implies that the phase should be 2 pi lambda times delta R, but clearly in this case, delta R is equal to 0, so I get 0. This immediately tells me that these guys, these waves here, the waves are in phase. And that means here that if I have a wave like this, then the other wave is right in sync with it like this. They're in phase. So there's two ways to interpret this. So if I have a path difference of 0, this also implies that the phase is 0. They're one and the same. Now let's go to the next picture. If I go to the next one, I'm going to say MC equal to 1. And what does that mean? Well, according to our relationship up here, our relationship says if MC is equal to 1, then the path difference must be a wavelength. So that implies here then that the path difference is a wave. So that means here that the speakers are separated by 1 wavelength. So I have to separate them. Okay, I have to separate them. So here we go. So now I have my first speaker right here. And I have my second speaker, let's say right here. So now what you're seeing here is that these are separated from each other. So that means that if I measure the distance from here to here, this distance between here and here is delta R equal to 1 wavelength. So what does that mean? You can see that source 2 travels farther than source 1 by 1 wave. So now if I was to bring this all the way here, these waves, this is traveling farther by 1 wave, and then it's looking like this here. So then the green source, you could see here, is in sync with this wave. Okay, so that means here, what I'm really saying is that if I compare, so if I look at this guy here, if I look at this here, you're seeing here is that at these 2 points, the crests of the blue and green waves line up. So following the same process as before, what does the path difference equation says? That means here that this phase is going to be 2 pi lambda delta R, and then this guy, we now know that from what we've already stated here, that this has to be a path difference of lambda, which then gives me 2 pi. In other words, if I say 1 wavelength, that's equivalent to saying that the phase is also 2 pi. Let's go to the next one. If I go to 1, 2, 3, oh, come on. Thanks. So now I'm going to pick MC equals to 2. So that immediately tells me that delta R has to be 2 waves. So now we know that the speakers have to be separated by 2 wavelengths. So then if I look at my green, let's say that it's over here now. And then I look at my blue. That means that the separation of the speakers here tell us that delta R must be 2 wavelengths apart. So then that means here is that I need 2 waves. Here's 1, here's 2, and then the waves continue after that. So then the green wave is in phase with the other wave. And again, you can see here is that the crests are matching up here. So again, from our phase equation, this has to be 2 pi lambda delta R, but now delta R is equal to 2 lambda, which then gives me a phase of 4 pi. In other words, delta R equals to 2 lambda is the same statement as the phase equals to 4 pi. So now we're seeing a pattern arise. Okay, we're seeing a pattern. So my pattern here reads something like this. I have MC. Okay, so if I have my MC, okay, let me try this again. So imagine that here's my MC value. And these values are going to be 0, 1, 2, 3, and they just keep going on. And then if I look at my path difference, delta R, you could see that this will be 0 lambda, 2 lambda, 3 lambda, and it continues on. And then if I look at my phase, then this will be 0, 2 pi, 4 pi, 6 pi. So my table is showing the pattern that's occurring. So now we can summarize constructive interference. We could say then that the path difference must be MC lambda, where MC is equal to 0 plus or minus 1 plus or minus 2 plus or minus 3, all integers. Or I could say that the phase can then be also 2 MC, let me be careful, 2 pi MC, and it tells me exactly the same thing. Now, let's draw a picture for destructive interference. So now let's go to 2. And what path difference is required to cause destructive interference? So just as we did above, we can say that earlier we showed that for maximal destructive to occur, the phase had to be odd multiples of pi. So we said that phi here had to be plus or minus pi, plus or minus 3 pi. And one way that we can write this is we can write this as 2md plus 1 times pi, where my m value, I put a little d to separate constructive and destructive. Now, this is going to seem a little bit odd, but there are 2 zeros. There's a plus or minus 0, plus or minus 1, plus or minus 2, and it goes on. And I'll explain what do I mean by that. But maybe I shouldn't put that right now. I'll separate it and I'll explain here in a minute. I'm really looking at the pattern. So now, if I put this all together, you see here is that I've now defined an m value that has a little c and a little d to remind you we are talking about constructive or destructive interference. So from the path difference equation, we see here is that now the phase has to be 2md plus 1 times pi, but that also has to equal to 2 pi lambda times delta r, which then tells us here that in order to have destructive interference, the relationship has to be 1/2 lambda times 2md plus 1, where again md is equal to 0 plus or minus 1 plus or minus 2, like this. So as we did before, how does this look like picture-wise? So we'll do the exact same thing that we did before. Now what we found here is that if I now look at this case here, I'm going to set md equal to 0. So according to our relationship, if md is equal to 0, I'm going to get 0 plus 1, which then gives me that the path difference must be 1/2 lambda. So again, what this tells us here is that the speakers are separated by 1/2 lambda. So let's draw them out. So if I have this speaker here, and then I have this speaker here, that's probably a little too close, so let me move this just a tiny bit. Maybe about right there. We can see here's my speaker 1, and then the farther one is 2. And what I'm seeing here is that from here to here, that path difference is 1/2 a wave. So what does that mean? That means if I compare my wave, this wave is coming here, and then it's oscillating like this, and then my green wave is starting here and oscillates like this. You can see how these guys are overlapping again. You could see as this goes up, this goes down, and you get cancellation between the waves here. So if I pick one point here, let's say I pick this point right here, you can see here is that the crests of the green and blue waves are out of phase by 180 degrees. So what does the phase tells me? So the phase factor tells me that it must be 2 pi lambda times delta r, but in this case, delta r is 1/2 a wave. So when I plug that in, I get a value of pi. So in other words, delta R equal to 1/2 lambda is the same as saying that the phase is equal to pi. So if I look at the next one here, I could then come in and then write that if I have MD equals to 1, then what I'm going to see here is that according to what we've written before, this has to be 3/2 lambda. So this says that they're separated by 3/2 lambda. That is the speakers. So if I look at them, I imagine that I have a speaker here, a speaker back here, and so if I start to that means the path difference between these two speakers is delta R equal to 1.5 wavelengths. So if I look at my waves now, so then this has to be half a wave, and then it has to be, oops, that's two. I think that's too much here. So I need to have 1.5 waves. So I got to go 1, and then I got to have my half right there. And then we then start the process of then them being out of phase again and again, continually out of phase. So once again, you're seeing that as this goes up, the blue is down. And the consequences is that you have destructive interference. So if I now look at the phase, this is going to be 2 pi lambda times delta R. Delta R is in 3/2 lambda. Then if I punch that in, I'm going to get 3 pi. In other words, whether I say it this way, in terms of path difference, or I say it in terms of phase, they're one and the same. Sometimes it's convenient to talk about something else versus another thing. So writing out the pattern, so writing out the pattern for destructive is I'm going to have my MD value, I'm going to have my path difference, and I'm going to have my phase. So when I look at this, you could see here that this is going to be 0, 1, 2, 3. And then here, I'm going to be half a wave, 3/2 of a wave, 5/2 of a wave, 7/2 of a wave. Look at the odd multiples of half wavelengths. And then if I look at my phase, this will be pi, 3 pi, 5 pi, 7 pi. So I could then say for destructive interference condition, that means that this guy here, delta R, has to be MD plus 1/2. Oh man, maybe I should have written, there's a couple ways to write this. I think I'm going to keep it this way. This is a little bit nicer, where MD is equal to 0 plus or minus 1 plus or minus 2, or I can write my phase where this has to be 2MD plus 1 times pi. Both of these say the exact same thing. Now what we want to do is we want to define this in terms of intensity, okay? So now what I really need to look at is I need to look at the intensity. Let me be careful. I want to look at interfering light waves and intensity. So here's what we want to look at here. So if I briefly summarize, we've said this, that for two traveling waves, right? For two traveling waves, we said that for two traveling waves, the amplitude is then going to be 2a cosine of 1/2 phi. But we don't measure amplitudes, okay? We do not measure amplitudes. What we measure is intensity. So when I look at the intensity, we see that the intensity, which is the amplitude squared, has to be 4a squared cosine squared of 1/2 phi. We are usually, not all the time, we are usually most interested in the relative intensity. I relative. So what does that mean? So let's look at this carefully, because a lot of people have a tendency to mess this up. So the relative intensity is then going to be the intensity at some location divided by the initial intensity, okay? So this intensity right here, this is for the superimposed waves, and this is for a single intensity. A single wave intensity. So when you look at this, look how we define it. We say that this is going to be 4a squared. Then I'm going to get cosine squared of 1/2 phi divided by a. Now, look at that 4. What we do here is that this 4 right here is absorbed into the definition of intensity. And what that means here is that we translate this guy so that we want to say that the intensity is only equal to cosine squared of 1/2 v. Once again, that 4 gets absorbed into the definition of relative intensity. So if that's the case here, then we could start to summarize everything here. So if I come over here, then we say that for maximal interference, we rely on v equals to 2 pi lambda delta r to determine whether it's constructive slash destructive So then we say that delta r, its nth path difference could either be mc lambda, or it could be md plus 1/2 lambda. And of course, this will be constructive, and this will be destructive, right? This is our path difference, right? So in this case, this is our path difference. Or we could claim here that the phase, depending on what we're looking at, is going to be 2 pi mc or 2 md plus 1 times pi. And again, we have constructive where mc and md have the exact same values. Right, and this would be our phase difference. So now let's look at let's look at light waves. Oh, wait. One more time here. I forgot to say. So if I look at the intensities, the intensities are I relative for construct. Let me be careful. So if I look at I relative, it's going to be 1 if it's constructive, or 0 if it's destructive. And you can see here why it's important to set the intensity to be cosine squared of 1/2 v. Now, let's apply this to light waves. So if I now apply this to light waves, their amplitudes their amplitudes is the strength of the electric field. So in other words, my amplitude now is then going to be 2 times E naught, the strength of the electric field, cosine squared of 1/2 V, which then tells us that now the intensity function is then going to be I relative will be cosine squared of 1/2 V. So if I continue to interpret this for constructive / destructive interference, we have that I relative, this, if it's 1, then we know that this is constructive, which means you see a bright spot. If you see 0, or you calculate 0, that means destructive, which means here that this is a dark spot. Or I could have I relative equal to cosine squared of 1/2 V, which then really implies, this all implies that I have limits to the range of I relative. That is between 0, the minimal, and its maximal right there. So what we're seeing here is that the interfering light waves gains a phase because there is a path difference.